Welcome back to physics. This lesson is all about braking and stopping. So this lesson is going to be relevant to anyone who plans to drive in the future. Pause the video, have a go at the quiz. Ready for some answers? Number 1, those are all speed limit signs. The first 3 are pretty obvious. The 50 means 50 miles per hour. And the white circle with the black diagonal line through it means national speed limit applies. So when you're driving, you have to know for each type of road what the speed limit actually is, because you don't get signs everywhere. Number 2, I'm sure you could think of lots of reasons. There's more children around, they're a bit less aware of the traffic, and if you've got a lower speed limit of say 20 miles per hour, you can stop in a much shorter distance than you would if you were going at a faster speed. And number 3, we're going to go through in a minute. It's a guideline for making sure that you are far enough behind the car in front of you when you're driving. So let's look at that one. So tailgating is when you're driving too close to the car in front of you, which means if they had to stop in an emergency, you might not be able to stop in time and you might hit them. 2-second rule is explained in the second box there. It takes about 2 seconds to say the phrase, "Only a fool breaks the 2-second rule." So if the car in front of you passes a street light or something, you start saying, "Only a fool breaks the 2-second rule," and if you pass the street light before you're finished, then you're too close and you have to back off a little bit. So here are the stopping distances from the highway code. So 20 miles per hour, it takes about 12 metres, that's 3 car lengths for an average car to be able to stop. And those increase quite drastically up to 70 miles an hour there, where it takes about 96 metres for a car to stop. So on the motorway, you should be at least that far away from the car in front of you. And it's quite difficult to judge distances, which is why the 2-second rule is quite useful. It's much easier to judge the time than to judge a distance. So the stopping distance is how far your car travels after you see a hazard and realise you have to brake. And it's made up of 2 parts, because when you see, for example, someone run out into the road in front of you, you don't put your foot on the brake straight away. You've got an initial moment of processing what you've just seen, and that depends on your reaction time. So we've got the thinking distance. That's the distance you travel at the same constant speed during your reaction time, during your thinking time. And that's before you even get your foot on the brake. After that, you've got the braking distance. That's how far your car travels while your foot's on the brake before it actually stops. So those 2 parts are going to be important. The stopping distance is made up of those 2 distances, the thinking distance and the braking distance, added together. And I'm going to show you another graphic now. So this one breaks the stopping distance down into the thinking distance there in blue and the braking distance there in red. Now the numbers might be a bit difficult to see, but don't worry, I'm going to turn that into a table and a graph later on so you can see it a bit more clearly. But you can probably tell from this, if you look at the thinking distance numbers, they go up 6, 9, 12, 15. They're going up 3s every time. Every time the speed goes up by 10 miles per hour, the thinking distance goes up by 3. And that's a sign of direct proportion. And we're going to look at that in a little bit more detail. So here's the same graphic again. Now, the thinking time depends on your reaction time, and it does vary a bit. There's no standard reaction time, but it's usually between about 0.2 seconds and 0.9 seconds. And that's affected by anything that will affect your brain or your attention. So if you're tired, if you've taken drugs, I don't just mean illegal drugs, I mean there are plenty of legal drugs, prescription medications, where it says do not operate heavy machinery on the back of the bottle or the back of the packet. That basically means don't drive, your car is heavy machinery. Alcohol, that affects your reaction time. And distractions. So all of those things will make your thinking time longer, which means your thinking distance will be longer and your stopping distance will be longer. And as I said there, thinking distance is directly proportional to speed. So let's look at that in more detail. As I promised, here's a table with the numbers in it. I just want you to look at the speed and the thinking distance, the two columns in bold there. You can ignore the rest for a minute. In fact, I'm going to cover them up with a graph. There we go. So there's a graph of the thinking distance against the speed. And as you can see, it's a straight line that goes through the origin. Therefore, the relationship between thinking distance and speed is direct proportion. And that's a phrase examiners love to hear. If you get an exam question and it's got a straight line graph on it like that goes through the origin, I want you to write down somewhere on the page, on the graph if you like, this graph is a straight line through the origin. The relationship is direct proportion, because it's going to come up somewhere in the question. Now, you probably did an experiment, possibly in biology, about investigating reaction time. So that might look a little bit familiar, where you've got two people, one person holds a ruler, the other person is going to try and catch it as soon as you see it drop. However, the kind of thinking time or reaction time you might measure in the lab is probably going to be different. Can you think of a reason why? Just pause the video and think, if you were driving along, why might your reaction time not be the same as what you'd measure doing an experiment like this? Okay, you might have come up with the idea that when you're driving, you're not actually thinking about stopping. You might be listening to the radio, you might be concentrating on things that are going past you, you might be thinking about the traffic lights up ahead. You're not maybe expecting there to be an obstruction in the road or someone jumping out. So you're not prepared to stop. Whereas an experiment like this, you can practice it a few times and you probably find that if you practice it, you get better. All right, that's enough about thinking distance for the moment. I want you to pause the video and do activity 1 from the worksheets folder. Ready for some answers? So breaking distance, that's straightforward. For the graph question on 1b, if you said as the speed increases, the thinking distance also increases, that on its own only gets you 1 mark. If you said it's direct proportion, that will get you 2 marks. If you said as speed increases, the thinking distance also increases by the same amount every time, that would get you 2 marks because you're implying direct proportion. But really, direct proportion is a 2-word phrase that sums up the whole relationship. Part C. Part 1, that's a control variable. That's the things you keep the same all the time. Part 2, there's 2 separate marks here. 1 mark for implying that you have to do the experiment again, but with music playing. And then a mark for saying you have to compare the results with and without music and look for a difference. Part D, reaction time increases. And part E, which one of the cars stops in the shortest distance? So we've got velocity time graphs. So we'll do a bit more about velocity time graphs in a minute or two. Let's look at the features of these ones. They all start at the same velocity, that's 13 meters per second. And they all have the same thinking time. That little horizontal line is showing continuing at 13 meters per second for the same length of time. However, car Y takes the least time to stop. Therefore, it must be the shortest distance. Let's look at braking distance now. Remember, that is the distance your car travels once you've slammed your foot on the brake. So that's going to be affected by anything that will affect the condition of the road or the condition of the brakes or the condition of the tyres. But if you get a question about it, you have to be really specific on what you say. So road and weather conditions such as wet or icy roads. And vehicle conditions means worn brakes or worn tyres. So if you get a question that says, explain what would affect the braking distance, you can't just say the weather. You've got to be specific and say, if it's icy, the braking distance will increase. Now, when your car is moving, it's got kinetic energy. Remember, half times mass times velocity squared is kinetic energy from the energy topic. It comes into forces as well. And work done was also in the energy topic, but it comes into forces as well too. Now, work is done by the force of friction between the brakes and the wheel. And that work is being done over the whole braking distance. And that reduces the kinetic energy of the vehicle. The faster the vehicle's travelling, the greater the braking distance will be because there's more kinetic energy. Can you think of anything else that might affect the braking distance? Think about the equation for kinetic energy. And what do you think is the relationship between the braking distance and the speed? I mean, obviously, as the speed increases, the braking distance gets longer. We've just said that. But could you put more detail on that? Well, what else might affect the braking distance? The mass. If the car has a greater mass, or if you've got extra passengers in it, then it's going to have a longer braking distance because there will be more kinetic energy because the mass is higher. So the same car with just you driving it will have a shorter braking distance than the same car with you, your entire family, and all your luggage when you're going on holiday, because the mass is much greater. Let's have another look at braking distance and speed. This is higher tier, okay? So, again, ignore the two columns that aren't braking distance. We're just looking at speed and braking distance now. You can see that it's not going up the same amount every time. You know, the thinking distance went up in 3s. The braking distance isn't going up by the same amount. You know, 6 to 14 is 8, then 14 to 24 is 10, then 24 to 38 is 14. The increments are getting bigger every time. Now, if we plot the graph, it looks like that, it's curving up. So you can see that as the speed increases, the braking distance is increasing, but it's increasing by more and more all the time. So how could we prove that braking distance depends on speed squared? Where on earth are you getting that from, miss? I hear some of you say it in your heads. Well, kinetic energy is a half of the mass times the speed squared. Work done is force times distance. In this case, that little s would be the braking distance. So if the kinetic energy equals the work done, then a half mv squared equals the braking force times the braking distance. So the braking distance must depend on the speed squared. But how can we prove that using the numbers? We've got a choice. We can either say, well, if I do distance divided by speed squared, do I always get the same answer? Or you could say, what if I plot a graph of distance and speed squared? Do I get a straight line through the origin? That's two approaches you could take. And I'll tell you now, if you work it out, the one in green there, distance divided by speed squared, you always get about 0.015. So yes. And if you plotted the graph, you would get a straight line through the origin. So that shows that the braking distance is proportional to speed squared. And that's going to come up a little bit later in a simpler form in one of the past paper questions you're going to do. Okay, other factors that affect the braking. Well, work is done by friction, and you know that friction causes surfaces to heat up. If you weren't sure of that, rub your hands together, they'll get warm. So friction will increase the temperature of the brakes. If you've got a very large braking force, you'll get a large deceleration, and that might make the brakes overheat and jam, and your car might skid. And modern cars generally now all have anti-lock braking systems to prevent this. So here's a quick reminder of what we've done so far. There's a definition for the thinking distance and a definition for the braking distance. And stopping distance is those two distances added together, thinking distance plus braking distance. So the stopping distance graph looks kind of in between the straight line and the curve that we had before. So it's a curve like the braking distance graph, only a little bit flatter. All right, pause the video, have a go at these questions. Ready for some answers? All right, define stopping distance, thinking distance and braking distance if you weren't sure on that. There we go, it's in that lilac box. 3 factors that affect braking distance. You could have said worn brakes, worn tyres, slippery surface of the road, for example, ice or rain. State whether each of the following would affect the thinking distance or the braking distance of the vehicle. Ice on the road, braking distance. Alcohol intake of the driver, thinking distance. Tiredness of the driver, thinking distance. Petrol spills might make the road slippery, so that would be braking distance. Right, let's look at the velocity time graph for stopping a vehicle. We already know a bit about velocity time graphs, so we're going to apply that to this situation. So here are my axes, velocity and time. Initially at time equals 0, that's when you see the hazard on the road, and you're still going at a constant speed until your brain has had time to process what you've seen and tell you to get your foot on the brake. So you keep going at a constant speed during your thinking time. And there we go, if you drop a line down onto the time axis like that, you can find out what the thinking time is. After that point, you get the brakes on and you decelerate. And a reminder about how we use velocity time graphs. The gradient of that sloping bit is the acceleration. And also, think about this for a minute, distance is velocity times time. So if you've got velocity on the y-axis and time on the x-axis, what you're doing when you do velocity times time is you're working out an area from the graph. So that means the area of that red rectangle is the thinking distance, and the area of that triangle bit of the graph is the braking distance. And if you add those together to work out the total area of the whole graph, that's the stopping distance. So that's going to come up in past paper questions as well. Working out the area underneath is higher tier. So if you think you might be doing foundation, don't worry too much about that bit. Have a go. But don't stress about it if you're not too sure. All right, so here's a worked example. Now I've saved the slides with these questions on as activity 2. So if you want to pause the video and have a go at activity 2 from the worksheets folder and then come back and check your answers, that's fine. If you want me just to talk you through how to do this question, just keep playing. Again, that's absolutely fine. You could print out the activity if you wanted and write in the answers as we go along, and that will give you something to help you when you're trying to do yours independently. Okay, so we've got some information about the highway code up there. We've got a graphic to show the thinking distance, the braking distance and the total stopping distance. we've got the reaction time of the driver is 0.7 seconds, two factors which could increase a driver's reaction time. I went for alcohol and drugs. You could have said distractions and tiredness. What effect does an increase in reaction time have on thinking distance? It increases the thinking distance. The braking distance has no effect because braking is not to do with your reaction time. It's to do with the force of the brakes. And total stopping distance must increase. Explain why braking distance would change on a wet road. It's 2 marks, so we need to make 2 points. First thing, it just says in the question, explain why the braking distance would change. We need to say how the braking distance would change. So the braking distance would increase and then give a reason, because there's less friction between the tyres and the road. So we've got a car travelling at 30 metres per second. The driver braked. The graph below is the velocity time graph showing the velocity of the car during braking. So this is a braking graph, but it doesn't have the thinking distance bit on. It's just got the sloping line for braking. Calculate the rate at which the velocity decreases. That's the deceleration. So we have to know to take data from the graph, and we have to know our equation for deceleration. So there we go, we've got an initial velocity of 30 metres per second and a final velocity of 0 because it's stopping. We've got the equation A equals V minus U over T, and the time was 4.8 seconds. Substitute in the numbers. That gives you minus 6.25. Because the question says give us the deceleration, if I drop the minus sign, I won't lose a mark. You can leave it in and you won't lose the mark either. It's up to you. Now we've got the acceleration, we're being asked for the braking force. F equals ma. We've got the mass is 900. Multiply that by the acceleration we just worked out. We get 5,625 newtons. It doesn't say anything here about number of significant figures, so we can give the whole thing. And then the braking distance. We need to get that from the graph, so I'm going to get my graph back up here. Now the braking distance is the area under the graph. It's a triangle, so it's a half of the base times the height. I can't use my ruler to work those out. I've got to use the values from the scale. The base is 4.8, the height is 30, so that gives me 72 metres. 1 mark for knowing you've got to find the area. So if you've written anything that shows you're trying to find the area of that triangle, you'll get 1 mark, and 2 marks if you get the answer. Here's another worked example. This one's a bit tougher. What we have to do is turn that little story for question 1 into a graph. So I'm going to give you a few seconds just to read that. All right, let's go through what information we've been given. Drivers driving along a road at 30 metres per second, so our graph has to go up to 30 metres per second on the speed axis. We've got the reaction time is 0.67 seconds and another 5 seconds on top of that, so our graph on the time axis has to go up at least to 5.67, makes sense to go up to 6. We're told there's a constant braking force, that just means it's going to be a straight line on the graph. All right, so I'm going to use the whole of the graph paper that's provided to go up to 30 metres per second and along to 6 seconds. Then I need to find where 0.67 is. Now this was a bit awkward. Mine might be a little bit inaccurate because I'm trying to write with a stylus on an iPad mini screen, so it's not very big. In the exam you get quite a large graph to do this. So there we go. There's our constant speed of 30 meters per second as far as the thinking time. After that point, it takes another 5 seconds. So I've got to go to 5.67 because it says another 5 seconds. Got to add that on. And then a straight line, as you can see, I missed. Obviously, in the exam, you would have a nice sharp pencil and a rubber and a ruler and you'd do it perfectly. So I wouldn't get 5 out of 5 for that because I missed with my sloping line there. But 2 marks for getting both axis scales correct. Now, if you did your graph halfway, so see where I've gone up in 5s, if you'd gone up as 10s, you would lose a mark. And where I've gone up to 6, if you'd gone up 2, 4, 6 and stopped halfway, you'd have lost a mark. And then 3 marks for getting those 3 points on the graph correct and straight lines between them. As I've said, that bottom green tick for where the line crosses the axis, I wouldn't have got that because I haven't done it carefully enough. Okay, calculate the acceleration. We're just taking values from the graph. We're starting at 30 meters per second. Final speed is 0. That took 5 seconds. Put them into the equation and get your answer. This time it asks for acceleration. So I'm going to leave the negative sign in to show the examiner that I know it's actually slowing down. Here's another kind of question you can get. This time they've given us the whole speed time graph. So we're starting at 35 meters per second, see an obstacle at time t equals 0, the driver reacts and brakes to a stop. We have to determine the braking distance. So we want the bit of the graph where the braking is happening. And if you read across the graph there, it looks like that horizontal line ends at 0.6 seconds and the sloping line showing the deceleration goes to 4.6 seconds. So I need the area of that bit of the graph. So a half times the base times the height. A half times the base, well, from 0.6 up to 4.6, that is 4 seconds. Then the height was 35 meters per second. So a half times 4 times 35 is 70 meters. A mark for knowing you have to find the area. A mark for showing you've found the correct area by using the right numbers from the graph. And a mark for getting the right answer. If you had found the area under the entire graph, you would have got 2 out of 3 because your mistake would be not realising which bit of the graph you want. Part 2. If the driver was travelling at 35 meters per second on an icy road, the speed time graph would be different. Add another line to the speed time graph above to show the effect of travelling at 35 meters per second on an icy road and reacting to an obstacle. 3 marks. All right. Well, the road conditions don't affect your reaction time. So the first bit of the graph is the same. However, the road condition will increase your stopping distance, your braking distance. So the graph will look like that. The first bit's the same, but the sloping line is not as steep. It takes you longer to stop. All right, have a go at the Activity 3 exam questions. Spend about 20 minutes on them. You don't have to do every single question. They start easier and they get harder. So the first couple of questions are foundation and the kind of easy end of higher. And the last questions are the the more difficult ones. So you decide, look through them and you decide where you want to start. And then come back and watch the rest of the video to mark your work from the model answers. Breaking and stopping exam questions. Mostly. These questions are building on what you've learned in the previous videos as well. So we'll be bringing in quite a few different skills that we've learned. Okay, let's look at the first question. We've got a number of different forces acting on a moving vehicle. A car is moving at a steady speed with a driving force of 3,000 newtons. Now the fact that it's a steady speed, that tells me that there is no resultant force. That means if there's a driving force of 3,000 newtons forward, there must be another force of 3,000 newtons backwards to compensate. What causes most of the resistive force? Let's have a look. It's going to be air resistance. Car is moving along a road. The driver sees an obstacle on the road at time t equals 0 and applies the brakes until the car stops. And there we've got a graph showing how the velocity changes with time. Which feature represents the negative acceleration? That's the deceleration. So where is the graph showing the velocity decreasing? Well, that must be the gradient of the sloping line. Which feature represents the distance travelled by the car? That's the area. Now, on a different journey, the car is moving at a greater steady speed. The driver sees an obstacle at time t equals 0 and applies the brakes until the car stops. The driver's reaction time and the braking distance are the same. Okay, so we have to draw the graph. Now, if the reaction time is the same, then here's where the driver's reaction time was. I'm going to extend that line up a little bit because he started at a greater velocity. So we need to show a straight line up to that point. So the reaction time's the same. And then it says that the braking distance is the same as well. Now the braking distance is the area under this triangle. So we need another triangle that has approximately the same area. So instead of a wide, short triangle, we're going to have a taller, thinner triangle. Something like that. C. Thinking distance and braking distance affect stopping distance. Explain how the factors that affect thinking distance and braking distance affect the stopping distance. Alright, so we need to say what are the factors that affect thinking distance, what are the factors that affect the braking distance, and how do they affect the stopping distance. So the first thing that I'm going to do is say how are those related. So I can say stopping distance equals thinking distance plus braking distance. I can then discuss factors that affect each of these. So I could say, let's take thinking distance first. Thinking distance is increased. It's important to say whether you're increasing or decreasing. So where it says factors that affect thinking distance, say how it affects it. Thinking distance is increased if the driver is tired, has drunk alcohol, taken drugs, or is distracted. Instead of saying or is distracted, you could say something like is on their phone. Braking distance is increased if, and this is factors to do with the car, the tyres are worn, the brakes are worn, or the road is slippy because of rain or ice. Okay, so let's see, 6 mark questions so far. I've said factors that affect the thinking distance and how they increase it. I've said factors that increase the braking distance. Ideally, I want to give a little bit more information. I've said how stopping distance is related to those two. What have I not said? I've not mentioned speed. So I could say both the thinking distance and the braking distance increase if the speed increases. There, I've given quite a lot of information there. Let's see, other things we could have put in for some additional information to get us up into the 6 mark bracket. I could have defined what thinking distance was. I could have defined what braking distance was. So for 1 or 2 marks, we'd be looking for just 2 or 3 factors that affect thinking distance or braking distance. For 3 or 4 marks, we're looking for an explanation of how the thinking distance and the braking distance are affected. And for 6 marks, we're looking for all of that, plus some extra information. So in my case, the extra information is about speed and is about how they're related. You could have said thinking distance is the distance your car travels while you haven't put your brakes on yet. Whereas braking distance is the distance your car travels after you've braked. That would be some extra information you could put in to make sure you got those 6 marks. Right, question 2. Hope this one wasn't too challenging. That was driver's reaction time and braking force. Which would not increase the thinking distance? The state of the car tyres. We've got a graph showing the braking distance and how it changes with speed. And first question, what conclusion about braking distance can be made from the graph? Now in the earlier part of the video, the main part of the video, there's a bit in there about how braking distance and speed are related. So for 1 mark, you could just say, as the speed increases, so does the braking distance. You could give a little bit extra information for 2 marks. You could say, as the speed increases, the braking distance increases, but at an increasing rate. So the braking distance is increasing faster than the speed is, if that makes sense. So ideally though, I'd be looking at using the data. So if we look at the graph at 10 meters per second, the braking distance was 10 meters. If we double the speed to 20 meters per second, the braking distance is 40. It's gone up by a factor of 4. So I'm going to use that in my description. I'm going to say, if you double the speed, the braking distance goes up by a factor of 4. And then I've shown on the graph where I got that data from. could have chosen 5 and 15 to say, well, if you got by a factor of 3 in the speed, the braking distance goes up by a factor of 9. You could potentially show that the braking distance depends on the speed squared, but it's quite difficult with a very small graph. The graph is for a car driven on a dry road. Okay, so we want to add a line on the graph for what would happen if the road was icy. Well, if the road was icy, your line on the graph is going to show that the braking distance is higher than it was. So we need a curved line that is everywhere above the line that is already there. Right, the question about the local council. So the councillor said it will be much safer because drivers can react much faster when driving at 20 miles per hour than when driving at 30 miles per hour. This is wrong. Why? Well, just because you're going faster doesn't mean your reactions are faster. Your car's faster, but your brain isn't. Your reaction time is not affected by your speed. Second part, the local council must decide whether to introduce the lower speed limit on a lot more roads. What evidence should they collect to help make that decision? Well, they need to know if reducing the speed limit will actually be effective at reducing the number of accidents. So they have to count how many accidents there are on the road before they reduce the speed limit, and then compare it with the number of accidents on the road in the same period of time with the lower speed limit. So you could say, count how many accidents there are in the same time period, or in a year. You could give a time period if you wanted. So let's get that down first. So you do that for the new speed limit, and then compare with how many accidents there were at the old speed limit. Okay, so one idea that you've got to count the number of accidents, and the second mark is for saying that you know you need to compare. Right, question 3. We've got a graph here of thinking distance against speed. It's a straight line through the origin. That should be telling you a phrase, 2 words. What is the relationship between thinking distance and speed? Direct proportion. If you just wrote direct proportion, that's all right. I'm going to write it a little bit longer. Thinking distance is directly proportional to speed. If you just wrote as speed goes up, the thinking distance goes up, on a foundation paper that might get you a mark, but to guarantee it, get the words direct proportion in there somehow. Okay, many people drive when they are tired. Draw a new line on the graph, so go back up to the graph, to show how thinking distance changes with speed for a tired driver. Okay, if the driver is tired, their thinking distance is going to be longer, it's going to be higher. So we need a line that is straight, starts from 0, 0, and is higher than the previous line. So any straight line up there is fine. Part 3. This is one where there's no mark for saying yes, no, or maybe. The mark is for the answer. So I went for, yes, it will be reliable, because the highway code is something that is checked by lots of people. So that's what I went for. You could have got the mark for saying no, because the data used in the highway code is actually quite old, and maybe it should have been updated because maybe cars have got better brakes now than they used to. Or you could have said no, because it only gives you values for an average kind of car, not for any particular cars. But the mark is for the justification. If you're not sure, then email your teacher and ask. Part B. The distance a car travels once the brakes are applied is called the braking distance. What's the relationship between these three things? Well, stopping distance equals braking distance plus thinking distance. So thinking distance plus braking distance equals stopping distance. You might have written it that way around. State two factors that could increase the braking distance of a car at 15 meters per second. That's things to do with the car on the road, so worn tyres, worn brakes, ice on the road. Now, things that you can't say here, you have to say the brakes or the tyres are worn. You can't just say they're old, because they can be old but perfectly functional. And as for road, you can't just say, oh, that it's something to do with the road surface. You have to be specific and say what's to do with the road surface, so ice or rain on the road. Right, so we've got a speed time graph here. So we've got a car driver seeing a dog on the road, has to make an emergency stop, and this is how the speed of the car changes with time after the driver first sees the dog. Okay, so I'm going to do some annotation on the graph before we start, because if they give you a graph like that, they're going to ask you about points A, B and C. So let's see, there's 20, there's 25, that point there is at 24. Let's see, point B, if I read that down, all the way down here, that's at 0.7. and that is at 4.7. Which part of the graph represents the reaction time or the thinking time? That's up here, from A to B. You need to give both letters. You can't say part A or part B. You have to know it's the line between them. What is the thinking time? There we go. 0.7 seconds. Calculate the distance travelled by the car in this thinking time. Well, it was travelling at 24 meters per second for 0.7 of a second. So we're using distance equals speed times time. So we get 16.8 meters. Calculate the acceleration of the car after the brakes are applied. Okay, so we need to get our data from the graph for this. So from the graph up there, we can see the initial speed was 24, so there's U. The final speed was 0, so there's V. And that took from 0.7 up to 4.7 seconds. So that took 4 seconds. So let's do a little list of our data. I'm going to put it over here. The initial speed was 24 meters per second. final speed was 0, time was 4 seconds, and we have to calculate the acceleration. Alright, our equation is A equals V minus U over T. That's from video number 2, I think. Let's put some numbers in. 0 minus 24 divided by 4, which is minus 6. Now, I'm not finished. Can you see why I'm not finished? What should be here? Calculate the distance travelled by the car during braking. Okay. The distance travelled, look at the graph up again, during braking is the area under this triangle bit. So I have to find the area of that triangle. So it's a triangle that's got a base of 4 and a height of 24. So I'm going to make it clear to the examiner that I know I want the area of that triangle. So it's a half times 4 times 24, which is 48. So a mark for showing you know that you have to work out the area, a mark for choosing the correct area, so getting the 4 and the 24, and a mark for getting the answer. The mass of the car is 800 kilograms. Calculate the braking force. Well, we know the mass, 800 kilograms. Earlier we worked out the acceleration was minus 6 meters per second squared. Work out the force. I'm going to drop the minus sign here because it's just wanting the size of the force. It says it's a braking force, so we know it's going to be backwards, which is why it would have a negative. You can leave it in if you want. And we're done.